In the next section, I want to show you how to finish off this algorithm because it turns out I lied a bit to you in the last section. We're not quite done yet. We did manage to get step 2 and 3 done in linear time, and I was not lying about that part. But the recursive call, I glossed over this briefly, and there was a reason for that. It doesn't quite match up. So that's the recursive subproblem is not quite the same as the original problem. In particular, I asked recursively to compute the ranks of certain substrings, a certain subset of all the suffixes. But that's not the same as recursing on some string and finding the rank array of that string, right? The original problem was, here's a string, take all its suffixes and sort them and give me the rank array. And now I'm asking you to do something like this. That's not quite matching the signature of the method. So we'll have to work around that. The thing is, we really like to recurse on a single string because that's what the method can do. And what we want is a single string that has only the suffixes starting at not a multiple of 3. That sounds a bit like a problem. It turns out it's not. You can do it with the following trick. So first of all, you take your string, and instead of looking at individual characters, you lump them together into triples. So I drew this by putting a box around them, but you should really think of ban as one super character that's now a single thing. It's one entity, a single character in a larger alphabet. And same for all the others. That's not enough. That gives you fewer suffixes now, right? Every suffix, by leaving off one more character, jumps 3 characters in the original string. So if we take this T box, then we get the suffixes starting at multiples of 3. If we want all the suffixes that don't start at multiples of 3, you can do this construction. You take the original text without the first character and apply this boxing. And then you append afterwards the string where the first 2 characters are omitted, and you apply this boxing construction. If you look at the suffixes there, that will be all those that start at either position 1 plus a multiple of 3 or position 2 plus a multiple of 3. And that's all that start not at a multiple of 3 in the original string. Okay. Again, a bit, why would you do it exactly like this? How do you come up with this? I don't have an easy answer for that, but it's doable, and the construction is a bit weird, but not particularly opaque. All that's involved is going to a different alphabet. You take triples of characters and treat them as one thing. So if we build this text T prime, we can apply the same algorithm recursively, and it will find the correct rank array. So it's not such a big deal after all. Now, as always, or as often, when you patch things up, when you apply the duct tape, you create other problems. And in this case as well, there is a problem that we created now. And the problem is, in each recursive step, we combine triples of characters into one super character. Now, if that doesn't sound scary, think of exponential growth, right? In the initial, you had maybe 10 digits, if let's say 26 characters in the first step. Now you cube that in the first recursive call. So it's 26 to the third, whatever that is. And the next step, you cube that again. Probably you do that 3 times and you're out of whack. You're in an uncomfortably big range. So why is that a problem? Well, we relied previously in the inducing step, we applied counting sort to these numbers. So if these become really, really large numbers, there's no more linear time sorting. So we can't do that. It turns out there's again a patch for that. And the reason is, okay, there may be many, many possible triples. but our strings are not arbitrarily big. Indeed, our T prime has at most 2/3 n different triples because that's the number of characters it has. So most of these triples that are theoretically possible don't actually occur in our strings. So what we do before we recurse is we reduce the alphabet to all the characters we really need. And we can do that because we're not really interested in the strings themselves, but only in their relative order in the rank array at the end of the day. So we look at all the triples that occur, we sort them, and we replace them by their rank. So again, we turn characters into numbers, but the numbers are from a small range. And so they will remain in the range that counting sort can be applied to in linear time. Effectively, we maintain that the alphabet size is at most the length of the string. That's a fairly reasonable thing to assume from the start as well. Let's see an example how this works. So both of these patching up steps together, just to make it concrete, same example as before. If I compute the T prime, I'm leaving off the first character here and then create groups of 3. And then I'm adding the same text, but the first 2 characters gone. So that's Bans Bananas Man. Okay, I'm not stuttering. That's the word, right? And you take triples, and so you already see like the triples have an offset, so you get all these suffixes. In this small example, there's only one triple that occurred before, so there's not too many duplicates. However, there's many triples of characters that do not occur, right? I don't see 3 B's or 3 M's or I don't know, 3 S's. All these don't occur. So you take those occurrent triples and sort them. Here they are in sorted order, and here's you can assign numbers to them, so it's just ranks in the usual way, like we always do, starting at 0. And so then you take your T prime and turn it into T double prime, where you just replace every triple with its rank. So A and N is here, so you replace it with the number 3. And that brings the alphabet size back to linear in the size of the text. All right. I don't know how clearly you see this, but that's really all we need. No more patches, no more duct tape needed. So first step is what I've shown you here. You construct a different text, again on a small alphabet, reasonably small alphabet, only of length 2/3 n. You recurse on that. What you get back is a rank array. You don't care that these characters have no connection anymore to the original text. The relative order is the only thing that matters. You get back this rank array R12. From that, you compute R3, and then you merge the two. Both steps take linear time. So that's the overall algorithm. All right. How good is this? Well, at least I claim to you so far. This is much sleeker just in terms of the space. If you're just storing the suffix array, it's n numbers, as opposed to n nodes potentially with sigma parent child pointers and so on. We have a fairly simple construction relying on just string sorting. Unless the text is super pathological, that will work fine. And you can do it in linear time. The different steps I showed you maybe look scarier than they are. If you code this up, it's really quick and easy because it's just manipulating integer arrays. And it's basically sorting with extra twists. Not much else happens in the DC3 algorithm. So it's very efficient in practice. And you can do efficient string matching with a log n overhead. But that's also a downside in a way. The theoretician at least feels the itching under the nails. it's m times log n, and we used to be able to do linear in m. Can't we kind of somehow get this back? And also there are other things in the suffix tree that we used before that seem gone for now.